Alright, in this video we're going to do a little review of limits and then talk about continuity. Let's start with this little graph. First thing, we're doing the limit as x approaches 2 from the negative side. So as we approach 2 from the negative side, we're approaching a y value of 2. Next, as we approach 2 from the positive side, so we're going along, we're approaching 2 from the positive side, we're approaching a y value of 3. So, the limit as x approaches 2, well, it's approaching 2 from the one side, approaching 3 from the other, so the limit does not exist. Remember, it must approach the same value from both sides. These two numbers here should be the same for the limit to exist, but they're not. Then, limit as x approaches 1. Well, as x approaches 1, so we're approaching a y value of 1 from both sides, so that's our limit. Now you may say, well, but the function's value is up here. It's 2. It doesn't matter. It's what value we're approaching, and we're approaching 1 from both sides. Okay, coming down to the bottom, the limit as x approaches 3. Well, if I plug 3 in, I get 1 over 0. Well, 1 divided by 0 does not exist. Remember, 1 divided by 0 does not exist. 0 divided by, let's say, 2 or 1 or 5, 0 divided by something, the limit's 0. The only time we have to do more work is when we get 0 on top and 0 on the bottom. We call that an indeterminate form, and we need to do something with that. Well, let's try this one. We plug in negative 3. Negative 3 squared is 9. Minus negative 3 is 12. Minus 12 is 0. Plug in negative 3 here. We also get 0. This is an indeterminate form, and we must do more work. So I'm going to factor the top. It'll factor to be x minus 4 and x plus 3. Okay, so let me just cross that out. And then you'll see that the x plus 3's will be gone because x plus 3 divided by x plus 3 is 1. Now we try again to plug in negative 3. Negative 3 minus 4 is negative 7. That is our limit. Remember, you must do more if you get an indeterminate form. The limit as x approaches infinity. Well, you see the highest power is on the bottom. Whenever the highest power is on the bottom and we're going towards infinity, the limit is always 0. We use those horizontal asymptote rules. High power on the bottom, the limit is 0. High power on the top, there is no limit. And same power top and bottom, we make a fraction out of the coefficients. So I think on this next one, we've got the limit as you go to negative infinity. But remember, a horizontal asymptote is both directions. It's what the function approaches. So I think I'm going to multiply the bottom out. So let's see, 1 times 2x is 2x. 1 times negative 3 is negative 3. Negative x times 2x is negative 2x squared. And negative x times negative 3 is positive 3x. So I multiply the bottom out. And I'm not even going to really bother to look at and combine like terms, because now I can see I have the same power on top and bottom. So I have 6x squared divided by negative 2x squared, so the limit is simply negative 3. It's just 6 divided by negative 2. So, continuity. A function is continuous if the limit as x approaches a of f of x is equal to f of a. Okay, now, this seems like kind of a confusing definition. It's essentially preventing us from having holes in our graphs. That if I plugged in a to my function, it'll actually work out. Remember, we've talked about it doesn't have to. We can have a hole in our graph, but to be continuous, we should be able to plug in a and just get the limit. Now, something is continuous at its endpoint, essentially if it's defined at the endpoint. So you'll notice up here, if we approach negative 5, we aren't defined at the endpoint. As we approach positive 5, we are defined at the endpoint. So on this side, you're continuous all the way to the endpoint, and at this side, you're not. Okay, you're not continuous at that endpoint. Now, the easiest way to talk about continuity is probably looking at the ways something could fail to be continuous. So we have 4 types of discontinuity, and I'm just going to draw some quick graphs, and I think you'll see that they're obviously discontinuous, and I think you'll see it very easy to identify. The first is a jump. We've got a function going along, and all of a sudden it jumps to another part of the graph. I think it's pretty obvious that is not continuous. That is a jump discontinuity. And if you want to look at the definition, the limit doesn't even exist here. So part of being continuous is that the limit's got to exist. It doesn't. The next is an infinite. Well, this is essentially just describing asymptotes. And I think we can all agree that that's not continuous because it spikes up, it comes down. Of course, it could be the same if it were spiking up, but any kind of asymptote we call an infinite discontinuity. And again, the limit doesn't exist there, so that's why we fail to be continuous. The next is oscillating. And we looked at one graph that had this. Remember, an oscillating function looks like this, where it kind of spikes back and forth. We don't even really know what's happening right here. It just spikes. We looked at that function cosine of 1 over x in class that did that. And if you don't remember it, graph it, zoom in on it near 0, and you'll see something very similar to that. Almost looks like a barcode. And again, the limit doesn't exist, so we aren't able to see it's continuous there. Finally, a removable discontinuity. A removable is one that's going along, has a hole in it, and then continues on. Okay? And that hole, the reason this is called removable is because the limit actually does exist here, but we have a hole. And remember, the definition of continuity is that the limit exists and the function's value exists at the same point. Well, here I have an open circle, so the function's value doesn't exist. If I had defined the function as something like up here, well, it's still not continuous because I have that hole. We call this removable because it's the one that's a little bit special because the limit actually does exist. In the first 3 examples, the jump, the infinite, and the oscillating, the limit doesn't exist, but in a removable, the limit does. It's just that the function's value is not defined as the limit. So let's look at how we can deal with that. We could deal with this with what's called a continuous extension. Now let me just first show you how we plug in 3, 9, minus 3, minus 6 is 0. Oh, it's also 0 on the top. So this is one where we'd say, well, it's an indeterminate form, so I'm going to factor the top. It's going to be x minus 3 and x plus 2. Then x minus 3 divided by x minus 3 is 1, so we can remove that. We can say, well, now we plug 3 in, 3 plus 2, so the limit is 5. So if I were to just graph what I've got so far, I'd say, well, it looks like the function x plus 2. That's what it looks like. Okay? But it has a hole at 3. Okay, at x equals 3. There's a hole because of this original problem in the domain. So I've got a function. We've got a y-intercept of 2. Okay, it's going up like this. But at 3, got a hole. We'll continue on from there. So it looks like that. Okay. Again, this is a removable discontinuity because we were able to find the limit. We know the limit is 5, but there is a hole there. But I could extend my function with a piecewise to fill that hole. If I said it's x plus 2 everywhere except 3, but at 3 it's 5, I have just filled that circle. And now I've made it continuous. Okay? So let me just go back here. We had to find the limit. We used our regular old trick of factoring. We got an indeterminate form. We found the limit was 5. So what we were left with after factoring and dividing out was x plus 2. So I graphed x plus 2, but I knew there was a hole at x equals 3, y equals 5, because in the original domain I couldn't plug 3 in. But I know the limit was 5, so I knew that was the y value it was approaching. So I extended the function with a piecewise part, and I said, well, it looks like the line except for 3, and at 3, I'm just going to define that one spot. It's got to be the same as the limit, and that made it continuous. So that's why it's called a continuous extension. You extended the function to make it continuous.